we can display information about a material's properties in the form of a stress-strain diagram, like the one that we see in front of us. So the example here is for what we call an idealized material. So in this case, an idealized steel. As we'll see in a moment, the actual stress-strain diagram that represents a more realistic type of situation is a little bit more complicated than what we see in the example here. But for starters here, we've got stress is being graphed along the y-axis, the vertical axis, and then the strain, which sometimes will be expressed as a percent, sometimes as a decimal, will be along the x-axis. And so when the material is in tension, stress is graphed as a positive value and strain is graphed as a positive value, whereas if we're under compression, stress and strain are negative. So we're in the first quadrant here when we're under tension, and we would have a third quadrant graph if we're under compression. So the yield stress, or sometimes referred to as the yield strength of a material, is that maximum stress that the material can experience before it experiences what we call plastic deformation. So we have elastic deformation, elastic strain is in this region here. So that's where the material is put under stress, and then once that stress is released, the material can rebound back to its original state. So that's what we call the elastic region of the graph. But once we exceed that yield stress or reach that yield stress, then the material is permanently deformed. It doesn't break yet, but it is permanently deformed, and so that's what we refer to as the plastic deformation region. So we have the elastic region, which is basically the triangle in here, and then we've got the plastic deformation that happens once we reach that yield stress and the material is put under commensurate strain. So the slope of that line, of the diagonal line that's cutting through the x-axis here through the origin, is the elastic modulus. If we think of our stress-strain equation, stress is equal to Young's modulus times strain. So if we're graphing stress along the y-axis and strain along the x-axis, the slope of that line in that plastic region is going to be Young's modulus. So in reality, a stress-strain curve is going to be a little bit more complicated than what we see in that idealized format. So we still have a linear section as shown here, which is our plastic region. So again, as long as the stress is not up to the level of this yield strength, then we have this linear graph where the slope is Young's modulus, and then the strain is going to be short of that yield strain. And so the material, once that stress is removed, will rebound back to its original position, its original state. Then we have this region where after we've exceeded the yield strength, it can still support without breaking or tearing or shattering or spreading, depending on if we're under tension or under compression. It can still sustain higher levels of stress than that yield strength, than that yield stress. It's just that once that stress is removed, the material will not be brought back to its original state. It's not elastic, but it's rather plastic deformation. So the material will be permanently changed. Once we reach the ultimate strength, so that highest stress level that the material can absorb, then we start to see the material start to yield. So if you imagine pulling on like a plastic bag or something, so there's a highest level of stress that it's going to be able to withstand, and then eventually the material is going to start to really stretch. Necking is what it's called, but ultimately that material is on its way to fracture, and then eventually the material experiences so much strain that it can no longer hold itself together, and so then it actually breaks, or again, under compression, shatters or spreads, so it can no longer perform the operation that it was doing before. Now again, for our purposes, the stress-strain curves that we'll be working with, the yield strain, once we reach that point, we're going to be horizontal, like what we saw in that idealized graph. So we're going to have these idealized graphs where the material is perfectly elastic in that elastic range, so basically what's underneath the triangle, and then perfectly plastic until we get to the point of fracture. So we're going to have that rectangular region for the rest of the graph. So in the example here, we're going to generate a stress strain curve for an idealized aluminum under tension. So that's why we're only dealing with the first quadrant, not the third quadrant. If we were under compression, then we would have a third quadrant graph. So we've got the yield stress, so our sigma yield is at 95 megapascals, and we have Young's modulus is this 110 gigapascals. So the first thing we're going to need to do is figure out what the yield strain is, because that's going to be the point on our curve. If we think about the examples that we had before, it's going to be the point in the curve where we're going to top out, so along the x-axis. We know that y-axis number is going to be 95 megapascals. The question is, what is the yield strain that goes along with that? So we can use our stress strain equation. So sigma equals Young's modulus times the strain. So we have 95 megapascals. So I'm going to express that in scientific notation here. So mega is times 10 to the 6th. So we're 95 megapascals. So it's going to be 9.5 times 10 to the 7th pascals is equal to, now Young's modulus is 110 gigapascals. Giga is times 10 to the 9th. So with 2 more decimal places, it's going to be 1.10 times 10 to the 11th pascals times our yield strain. So if we divide both sides by that 110 gigapascals, we're going to end up with a strain, yield strain of 8.64 times 10 to the negative 4th. Now again, that's dimensionless. Strain is a dimensionless quantity, length over length, but we're going to express it as a percent along our graph. So I'm going to report that answer as 8.64 times 10 to the negative 2nd if I move the decimal 2 places, or we can get away from scientific notation and express it as 0.0864%. And then the other key piece of information that we need is we have this fracture strain. So basically the point where the material is going to break is going to be at 0.2. So along the x-axis, if I have to go out as far as 0.2, judging by the pre-built graph that we have, we can count by maybe 0.04s or 0.05s. There's 0.04, 8, here's 0.12, here's 0.16, and here's 0.20. So this is as far out as we have to go. So that's our strain expressed in percent. Along the vertical axis, we're going to have our stress in megapascals. And so we have to go up as high as that yield strain of 95. So it looks like we can count by maybe 20s, 40, 60, 80, 100. So we'll be just short of that. So right here is our yield strain. So with yield stress. So with a yield strain of 0.0864, we're going to be just beyond that 0.8 spot there. So our graph is going to be linear through that region. And so the slope of that line is our Young's modulus. And then we've got this idealized graph, so we're just going to be straight across until we reach that fracture strain at 0.20%. And so here is our graph of this idealized aluminum under tension under these parameters.